Today we're going to be talking about permutations and combinations. So we need to know what a permutation and a combination is. So on the next slide we'll go over those. But before we do that, we have to talk about what factorial is. It says fundamental counting principle. That's incorrect. That should say factorial. The expression n factorial, or n with an exclamation point, is read n factorial. It happens when we do 5 times 4 times 3 times 2 times 1, or the value times the next lower, times the next lower, times the next lower, all the way until we get to 1. So 8 factorial will be 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1. That's the definition of what a factorial is. Not too difficult, but you do see that these numbers, as we start to multiply, will get very large very quickly. 5 factorial is already 120. We go 6 factorial, it's 720, and we just keep going from there. Why do we need to know about factorial? Because it's part of our permutations and our combinations. We have a different formula for each of them. They are very similar. Notice how this is written. It's NPR and NCR. N is the number of objects, and R is how many times we want to take it. So we read it as 5 things taken two at a time. 5 permutations at 2 at a time. N factorial goes on top, and n minus r goes in the denominator. For combinations, it's just a little bit different. We get still that n on top and the n minus r factorial, but we add an extra r factorial. And because we're dividing by more things, the combination is always going to be less than permutation. Permutations are bigger numbers, combinations are smaller numbers. Smaller being relative because we're doing a lot of multiplication here. So let's go ahead and talk about when we use them. A permutation is when order matters. When we're talking about people crossing a finish line, first place matters, second place matters, third place matters. There's different prizes or value with each of those. A combination is when order doesn't matter, when we can go ahead and order a bunch of things. You're out with a bunch of friends and you order 3 pizzas. Does it matter which one comes first? As long as they all come. Permutation order matters. Combination doesn't. All right, so let's look at a couple problems. Tell me whether the solution is a combination or a permutation. How many different ways can the president and vice president be chosen from 8 different people? So in order to figure that out, we would have to determine whether it's a permutation or a combination. Well, it very much matters whether you're a president or the vice president. So that's a permutation because the order matters. Are you going to get, which one are you going to get? Let's look at a combination. In an ice cream sundae shop, 9 different toppings can be chosen. How many different 3-topping sundaes can be ordered? So it doesn't matter if you have the hot chocolate, if you tell them hot chocolate sprinkles and whipped cream first, or you say sprinkles, whipped cream, and hot chocolate. They're all going to end up on your sundae, and it doesn't really matter which order you say it in. So combination is what this is. All right, let's use a permutation. The Reyes family is visiting a complex of theme parks near Disney World or something of that during their summer vacation. They have a 4-day pass good at 1 park per day. There are 7 different parks. How many different ways can they arrange their schedule? So we want 7 things chosen 4 times. So there's 7 different parks, and they can choose 4 of them. So that becomes 7 factorial over, and we're going to subtract this, 3 factorial. Well, 7 factorial is 7 times 6 times 5 times 4 times 3, all the way down. 3 factorial is 3 times 2 times 1. Notice they both have that 3 times 2 times 1. So those will actually cancel out, leaving me just the 7, 6, 5, and 4. Multiply those together, we have 840 different ways. All right, let's do another one. How many 5-digit numbers can be come from 2, 3, 4, 5, 8, and 9? Well, this problem is wrong. We have 6 different numbers here. Let's get rid of the 9 here. So we have 5 things taken 5 at a time. And order does matter. In a number, obviously, 1, 2, 3 is different than 3, 2, 1. So if it's 5 things 5 times, it's 5 factorial over 5 minus 5, or 0, or 1 factorial. We always just kind of write 1 factorial because it's 1. So 5 times 4 times 3 times 2 times 1, which is 720 different ways. All right, let's try another one that hopefully is a little better. How many ways can 5 runners be arranged in a 3-person relay? It very much matters who's going first, second, or third in a relay. So we have 5 things taken 3. We have 5 different people, and we want to take 3 of them. So 5 factorial goes on top, and we subtract this, that goes in the denominator, so 2 factorial. So we have 5 times 4 times 3 times 2 times 1, and 2 times 1. Those cancel the 2 and 1s, leaving us 5 times 4 times 3, which is 60. All right, now we have a combination. How many ways can a window dresser choose 2 hats out of a fedora, a bowler, and a sombrero? It doesn't matter with the order here, so that's why we switch to the combination. So what's the formula for the combination? It's three different things, 3 different hats, and we want 2 of them. So 3 factorial still goes on top. We still subtract them with the 1 factorial, but then we also have this value here, 2 factorial. Those probably should have been switched. It should have been 1 factorial times 2 factorial. Well, anyways, 3 factorial is 3 times 2 times 1. 2 is 2 times 1, and 1 factorial is just 1. Again, the 2 and the 1 cancel, leaving me just 3. So there's 3 different ways. They could do a fedora and a bowler and a sombrero and a fedora. How many different ways can a customer choose 2 pens, a purple, an orange, a green, a red, and a black? Well, there's 5 different pens. We want to choose 2 of them. So it's 5 factorial, and then we subtract them, so 3 factorial, and then 2 factorial. 5 factorial is 5 times 4 times 3 times 2 times 1. 3 factorial is 3 times 2 times 1 and 2 times 1. Again, those cancel, but we still have a 2 and a 1 on the bottom, which of course gives us the 2. On the numerator, we have 5 times 4, so it's 20 over 2, or 10 different ways, 10 different combinations. All right, the players listed here are playing tennis. If each player plays each other player once, what's the probability that Kyle plays in the first matches? All right, the order in which the players are selected is really not important. Whether I choose Thomas and then Carl, or Carl and Thomas, they're still playing against each other. So this is a combination. And I have 8 people, and I got to take 2 at a time. Only 2 play in the first match. So 8 things, 2 at a time. So it's 8. Subtract them is 6, and the 2 comes over. So 8 factorial is 8 times 7 times 6 times 5. 2 factorial is 2 and 1. 6 factorial is all 6 and down. Again, those cancel out. That's why I kind of have it that way, so that those cancel out, leaving me just 6 and 7, and the 2 in the denominator. 56 over 2, or 28 different matches is what we're going to have. Well, how many does Kyle play? Kyle plays every one, so that's 7 games. And the probability of Kyle is 7 out of 28, or 1/4. And that's what I have for you today.